Welcome to Chapter 5 Ethernet within the Cisco CCNA program. So today we'll be looking over Ethernet protocol, how LAN switches work, and how we use address resolution protocol to match layer 2 and layer 3 addresses together. So Ethernet is a encapsulation that is used around the world today. It's mainly used in LAN technologies, and the standards that cover this is 802.2 and 802.3. We can get up to 100 gigabits per second using this standard, but in most networks today we'll just be talking about 10 gigabits. So we use a combination between the physical and data link layers, and 802.2 specifically talks about the logical link control layer, sublayer of the data link layer, and 802.3 standard covers the MAC sublayer and the physical layer. So the LLC is responsible for controlling the communication between the software and the hardware. So to put it in Cisco terms, it controls communication between the upper and lower layers. And MAC is where we interface with the physical side of things. Sublayer, it encapsulates the data and controls how we access the media. Because this is modular, it has to cater for many different types of media. So we have lots of little standards for each type of media we're going to use. Within the data encapsulation, we have the frame delimiting, which is basically saying the start and end of the frame. The address, which has to be unique for each device, and error detection, which is basically a CRC check at the end. And then we have the access to the media itself. So Ethernet's been around since '73. It basically went down to 1 megabits per second. You can still find quite readily devices running at 10 megabits per second in legacy devices. A lot of the material you'll come across will talk about fast Ethernet, which is 100 megabits, and then today's material will talk about gigabit ports. So the frame is made up of various components, preamble being the start, then the destination, and then the source address, the type of Ethernet, which basically tells it what protocol it's working for, the data or the payload that it's transporting, and the checksum at the end. Your frame size can range between 64 bytes and 1518 bytes. Now, normally the average size is set to 1500 bytes. So anything over 1500 bytes will be considered a jumbo frame and discarded. Anything under 64 bytes is regarded as a runt, or where a collision has occurred, and will be discarded as well. Okay, MAC addresses in hexadecimal. A MAC address is a 48-bit binary value expressed in 12 hexadecimal digits. So basically this is where all that lovely binary to decimal to hexadecimal conversion worksheets that I've handed out come into play. Hexadecimal is used to represent MAC addresses, and we also use it in IP version 6. So basic hexadecimal runs between 0 and 9, and then A to F. So if you look on the sheets here, 10 becomes an A, 11 B, and so on to 15, which is the F. And when we deal with hexadecimal, we also deal with hexadecimal pairs. So a hexadecimal digit is represented always in pairs. So how's the address made up? It's made up of two parts. The first part identifies the vendor and is known as the organizational unique identifier, which is 24 bits. And then the second half is made up of a individual NIC interface identifier, which makes it a unique address for the MAC address. Now the vendor code is assigned by the IEEE, and the vendor uses the last 24 bits to stamp their cards as they are produced. Now, frames use these MAC addresses to identify the source and destination of the physical devices that need to process the frame. So unless the destination address matches the address on the network interface card, the frame is discarded. It's only when the destination address is matching the local interface card that it processes the frame and passes it up to the upper layers. If you look at the ipconfig/all command in the command window of Windows, we would see these addresses either represented with dashes or columns or periods, depending on the version of operating system and the type of operating system you use on your machines. Now normally with Ethernet we are looking at unicast addresses, and it's the same with the MAC addresses. We have one source to one destination, and that is why we have a destination and source address. Now we do have the occasion where we want to send it to everyone, which DHCP, ARP use broadcasts to get to every device. Now DHCP uses this to initiate the information being sent. The main one we'll concentrate in this chapter a bit later is ARP, which is Address Resolution Protocol. So basically when the destination MAC address is all Fs, or in binary terms all ones, every device on that network segment will pick it up and action it. So basically that's it for how a broadcast works. So the destination address is all ones, and that means every device within that network segment has to pick up and action the frame. The other occasion is when we have multicast addresses. This is where some, but not all, of the devices on the same segment need to action the frames coming in. So the multicast process has been assigned a particular vendor code, which is 01005E. So whenever a frame has that as the vendor code, it knows it's a multicast address and it needs to be picked up if it's set up for multicasting. So in here we also talk about the multicast IP address range is from 224 onwards, but we'll get into that more when we start doing the addressing of IP, which is in another chapter. In this lab, you will be expected to look at the MAC address tables within the devices so that you can see which way they are represented within the switch and the host, because each port on a switch has a MAC address as well as the connected end devices. 5.2 LAN switches, so we'll discuss how switches work within layer 2, and switches need to be able to make a forwarding decision based on the MAC addresses. Now these MAC addresses are learnt as frames pass through the switch. This is kept in a table and is known as CAM table, Content Addressable Memory. And the way it works is as the frame comes into the switch records the MAC address from the source field and puts that into the table, matching it with the port number that it arrived on. These entries are kept for 5 minutes before they time out and are discarded. Now, if there's already a corresponding entry within the table, then the timer is reset. What happens when it doesn't know the corresponding destination address? So there's no table entry for the destination MAC address. It needs to forward it out every port except for the port it received it on. And when a reply comes back, it will learn which port that particular MAC address resides on. So the next time the frame comes through and does the table lookup, it now has a corresponding destination address in its table and knows which port to forward it out of. So it will forward it out just that port and no other port. And again, another lab looking at the CAM tables within the switches, and they can also be found in end devices as well. Now, switches will forward information in two ways. They'll store and forward the frame, or they'll use a cut-through method. So with store and forward, it waits until the entire frame arrives, does a CRC check on the frame to make sure all of it arrived, and then starts to forward it. But when we talk about cut through, we need to determine which method or variant of cut through it uses. So with fast forwarding, as soon as the switch has enough bytes to determine the address that it needs to forward to, it'll start forwarding the frame straight away. The other method is fragment-free switching, which means 64 bytes has to arrive before it'll make a forwarding decision. This is to ensure that the frame isn't a runt, and so it adds a little bit of delay into the process because of that, having to wait for the first 64 bytes, but it's not that much of a delay. Now, to keep track of all this information as it's either stored and forwarded, or a little bit is taken in, like the 64 bits with the last session, we need to use buffers. Now, we've got two types of buffers on switches. We have port-based memory, which means for each port, both incoming and outgoing, there has to be a section of memory assigned to it for buffering. And once that buffer's full, it's full. The other type is shared memory, where all the frames first in, first out basis arrive at, and use a common pool of memory for buffering for all ports. Whereas under port based, each queue has an assigned memory size. So even if there's no traffic coming in on a particular port, it still has memory assigned for buffering on that port. Duplex and speed settings were manually set originally, so we had to assign whether it's full duplex, where both ends could talk and listen at the same time. Half duplex is where only one of them can send or receive at once. Now, a duplex mismatch is when one device is set at full and the other device is set at half. Now, that will require the devices to be reconfigured at one end, because they need to match. Because if they're not matching, you will have collisions occurring, because one device thinks it can transmit all the other device is, and it's not physically possible when one is set to half duplex. Auto MDX came about in version 12.2, where we detect the type of cable being used and auto negotiate the speed and duplex settings for that cable. So we can still get duplex mismatches and so forth, even with MDX being used, and this will cause the interface to flap, which is go up and down, and you fix that by setting one end to whichever mode needs to be used, whether it's full or half duplex. With address resolution protocol, we need to have a method of matching the physical address with a logical address. So our logical addresses come down into the data link layer via the packet. We then encapsulate it with our layer 2 addressing. Now the layer 2 destination address is referring to the next device that needs to process the frame. The layer 3 headers don't get changed until it gets to the final destination. That is not the case with the frame headers. So for each device that needs to make a routing decision, such as routers, the frame is removed, because as it comes into the receiving port on the router, that was its destination for the frame. The router will determine which interface it needs to depart on to get to its final destination, and this now becomes the source MAC address, and router 2's inbound interface becomes the destination MAC address. So we have a totally brand new header, framing header assembled, and we rinse and repeat on router 2. So in its journey from device A to the file server, we've had 3 layer 2 headers along its journey. And we'll use Packet Tracer in this lab to identify corresponding MAC addresses with IP addresses. Now, you can build those tables up manually, but it's not as efficient as doing it automatically. So with ARP Address Resolution Protocol, it sends out a request saying I need to get to this IP address. It's a broadcast, so every other device will see the frame and action. It will then pass it up to the layer 3. If it is the IP address that the device is looking for, it will send a reply back to the ARP sender saying this is my MAC address. And if it is not on the same network, the gateway will send back a reply saying this is the MAC address to send that IP address traffic to. ARP caches last for approximately 2 minutes. This can be changed. You can manually add or remove entries into ARP tables. An example of an ARP table, left hand side shows a router, the right hand side a Windows PC. So you've got the IP address, the physical address, and how it was learnt. Examining ARP tables is the next lab within the series for Chapter 5. So the ARP request is received by every device because it's sent out as a broadcast, and every device on the local network needs to respond or action to it. So the way it works is it picks it up, looks at the IP address. If it matches, it'll send a reply. Now, because it is a well-known protocol, people can use ARP spoofing to intercept the traffic So pretend it is the gateway and receive the traffic instead of the legitimate gateway. We use a system called dynamic ARP inspection to mitigate this type of attack in enterprise level networks. So in this chapter we explained the Ethernet operation, the switching functions available to us, and how we dynamically match layer 2 and layer 3 addresses so that communication occurs over a network. Thank you for joining me today. Enjoy your reading on Chapter 5. Please complete the labs and any corresponding worksheets. Thank you.